Right. Okay. So welcome back. So our second talk of the afternoon session will be given by Shir Peleg, who will tell us about Sylvester-Gallai type theorems for quadratic polynomials.
Okay. So this is a joint work with my advisor, Amir Shpilka. So I'll start with some introduction of the basic mathematical theorem, and then I'll give a motivation for the problem. So Sylvester-Gallai theorem is a very famous mathematical theorem. It says that if you have a collection of points in Rn that are not all on the same line, then there is one line that passes exactly in 2 points, okay, not in 3 points. Okay, so the contrapositive of this theorem, that if you have a set of points, that if you take 2 points, sketch the line that passes through them, and it intersects a third point from your set, then all your points are on the same line. Okay, they are collinear. Later, Cayley improved this theorem also to include points on the complex space. But in this case, there is an example of coplanar, that points that are plane but not on the same line, that satisfy this condition. But this is the worst case. So you know that the same condition applies, that your points are on the same plane. Okay? Now I'll just explain some extensions. Sorry, it's a little bit frightening, but bear with me. So actually, the Sylvester-Gallai condition is a local condition. You have 2 points and a third point that sits on the same line. Okay, so the first theorem is, what if this local condition, it doesn't satisfy for every 2 points, but every point satisfies it with delta of the other point? Then can you bound the dimension? And the answer is yes, and the dimension is approximately 1 over delta. So is another bound that we have. And the third, the colored version. So this is, we call the robust version, when the condition is is by a fraction. And this is the colored version. If you have 3 sets, that when you choose a point from one set, a point from another set, it intersects the third set. And so you have a collection of 3 sets that satisfy this property, then the dimension is at most 4. Okay, the dimension of the point. So this is like very old school, very interesting field of mathematics that is very, these are algebraic geometry questions. They study those kind of things. And what's really interesting about this problem is that the proof, it really relies on some geometry structure of the field. Those proofs are not correct for other fields, like finite fields, like the statement doesn't hold for finite fields, and even like algebraically closed field, it still doesn't hold. So it's like something about C or the complex field that is giving you this property. So for Sylvester-Gallai, we can use those algebraic questions that are somewhat equivalent. So if I have a set of vectors that every 2 span a third vector, the dimension of the set is at most 3. The only proof, well, not the only proof, but the main proof of this for years was a reduction to Sylvester-Gallai problem. This is an algebraic statement. Sylvester-Gallai statement is purely geometrical. So it's very interesting that simple algebraic question, the only way to prove it is using a geometry tool. And another equivalent question, if I have a set of linear forms, such that whenever 2 forms vanish, a third one also vanish, then again, the dimension of my set is small. And this is done by reduction to the first problem, that is done by reduction to Sylvester-Gallai theorem. So, and we can have the similar robust and colored version for those type of for vectors and linear forms. So, no, I know that there are some algebraic proofs, But like for many years, I think until like 10 years ago, it was only the geometrical proof for the first theorem. Now there is like a design matrices. I know about the design matrix proof. Yeah, that is, well, it's algebraic, but there are some, again, it doesn't work on any field. Yeah. So a very natural problem is taking the last theorem that I stated and asking it about degree R polynomial. So if I have a set of polynomial of degree at most R, that when every is vanish, then you know that the third one vanish as well, can you bound the degree of the dimension of set? And again, also colored and robust version are interesting. So as I said before, for R equals 1, this is exactly the Sylvester-Gallai theorem. Just one note, I call everything Sylvester-Gallai. There's no Cayley, there is no Cayley-Edelstein. It's all Sylvester-Gallai, because otherwise we will all get confused. So R equals 1 is the Sylvester-Gallai theorem. R equals 2 was proven by Špilka in 2018 for the regular case and the colored case as well. Okay, there was a proof. And R greater than 3 is still open. And the robust version for R greater than 2 is also open. So, yeah. So we can ask about, like, whatever bound you give is interesting, but we can ask the linear dimension. This is like what we will show. This is what Amir shown. And you can ask the algebraic rank. You can ask everything. We'll be happy to have any bound on give any structure for these polynomials. So why is this interesting? The Sylvester-Gallai problem for like linear form has many uses in locally decodable codes, in reconstruction of depth 3 circuits, and in polynomial identity testing. So I'll go over quickly the polynomial identity part. So this is the circuit, a depth 3 circuit. We have the size, the depth, and this is what we call a sigma pi sigma circuit, okay? So we want to find an efficient deterministic algorithm to determine if the polynomial that is computed by the circuit is the zero polynomial, okay? So let's consider a sigma pi sigma circuit where the top fan-in of the fan-in is 3, okay? So we have a polynomial of this sort, okay? So when we take some polynomial here, some linear form here, and some linear form here, and we zero them, we know that the product of the first vanish. Condition that is very similar to the Sylvester-Gallai condition, except that I have here a product of polynomials. But when we are talking about linear form, especially homogeneous linear form, let's from one assume everything is homogeneous, then this ideal is a prime ideal. So if a product of an element is in an ideal, one of them is inside the ideal. And so we have exactly a Sylvester-Gallai configuration, a colored Sylvester-Gallai configuration. So we can use Sylvester-Gallai theorem to get a bounded dimension of the linear forms. And then there are ways where once you have dimension bound, you can do efficient PAT algorithm, okay? And this is like the first basic PAT algorithm for such circuits. The best one uses like some sense of higher dimensional Sylvester-Gallai and then nothing that's related to it, but this was like the basic proof. So let us consider depth 4 circuits. So again, we have a sigma pi, but so again, we will consider the top fan-in is 3, and now I'll assume that the bottom fan-in is 2. So I have this product of sum of three products of quadratic polynomials, again, homogeneous. And so the same holds. If I take a polynomial from here and a polynomial from here, and I vanish them, then the first product vanish, if this is a zero polynomial, okay? And this is what raises the very interesting question question of Sylvester-Gallai theorem for higher degree polynomials. So if we had any bound on this set of polynomial, we could apply similar techniques and achieve PIT. So, but just in this case, the ideal generated by these two polynomial does not have to be a prime ideal, and it sometimes is not. And then I cannot reduce to the case of the theorem that I already showed you that Amir proved. It does not help us to solve the PIT problem, because I don't know that it must be the case that one of them is in the ideal. I need to have a product of polynomials in the ideal. And this is what raises the second problem, and this is the more interesting one, I think. So again, I have a collection of polynomials, but instead, when I take two polynomials, instead that there is one polynomial that vanishes, I have a subproduct of the polynomials that vanishes. In this case, can you bound the dimension of the set? So as I said before, R equals 1 is follows from Sylvester-Gallai and the fact that the ideal generated by linear form is prime. R equals 2 is our result. And the robust n colored is still open. And R greater than 3 is also open. So let me state our result. So we have Q, a set of quadratic polynomials, such that and I assume that they are pairwise linearly independent. Of course, it's a must-have in all the theorems, because otherwise the theorem does not hold. Take any vector twice, and it will hold. And I assume irreducibility. I will talk about it in the end, but I have a set of pairwise, linearly independent, irreducible, homogeneous quadratic polynomials. And then I have this, the condition that I said, like when every two polynomials vanish, there is a product that also vanishes. And from Nullstellensatz and the fact that I work over C, this is an equivalent condition, that there is a product in the radical of some polynomials. Okay? And I also switch it all the time. I say vanish, I say in the radical, it's the same, it's equivalent. Just one note, the irreducible is also crucial, and the statement is not true if I allow the polynomials to be reducible. Okay, so to achieve PIT, we need to work through this, but we'll talk it in the end. Yeah. So, okay, in my talk, dimension is linear dimension. Okay, every dimension that I prove is linear. So, proof. I'll go like the main points of the proof. So, I know in this theorem I have this local condition, and the first step was to understand this better. How can it be that a product of of several polynomials is in the radical generated by two other polynomials? So the first theorem is what we call the structured theorem, that takes this local condition and gives us a more concrete thing to work with. So if, again, I have a condition that I have two polynomials and two quadratic polynomials and a product of quadratic polynomials in the radical, then one of the following exists. Either one of the QK is in the span of A and B. This is a trivial case. Or A and B span a reducible polynomial, and reducible quadratic, it means that it's a multiple of two linear forms, okay? Or the third case, which I will explain by an example. So the first case, I just want to show you that all three cases are possible and they are different. So if I have A and B, I know that A plus B is in the radical. And so I can multiply it by any other polynomial, and it will be in the radical, okay? If I know that B is A plus C times D, so a reducible quadratic polynomial, then this polynomial is in the ideal generated by A. So let's think about it. When A vanish and B vanish, it means that A vanish and C vanish, or A and D vanish. So if A and C vanish, this is 0. And if A and D vanish, this is 0. So this product is in the radical, but none of them, none of them is in the linear span of A and B if I take it to. So this is a different case than the first one. And the third case, we mean that there are two linear forms, C and D, that both polynomials are in the ideal generated by C and D. So that means they are in the form x times C plus y times D. Well, all the letters are linear forms. They're not variables necessarily. So this is A and this is B. And then we can think about A and B as like the result of applying C and D in this matrix, right? So what happens? Either C and D are 0, and then this polynomial vanish, or they're not 0, but I know A and B are 0. I'm only interested in point when both A and B are 0. So that means that this determinant has a non-zero 0. So its determinant is 0. So I can substitute the determinant here, and then this product of those two polynomials vanish whenever A and B vanish, and this is the third case. Okay? But note that in this third case, the rank as the tensor rank, you know, in the tensor rank of quadratic polynomials, there is the tensor rank of quadratic polynomial is the minimal number of summands in which you can present as a sum of product of linear forms. Okay? And it's well defined, and it's the rank of bilinear forms that you study in linear algebra. It's similar, but not exactly the same. So, but actually in the third case, both A and B are of very low rank. Yeah, they are not rich polynomials. You know that there are like their rank is 2. You only need one sum to represent the polynomials. So this is what's interesting about this case. So how do we prove this theorem? Again, that I went from this local condition, and I proved that I proved that it must be the case that one of those three cases happen. Okay? So the proof consider the resultant of A and B in respect to some variable. Maybe, okay, never mind. So the resultant is a polynomial that it's the determinant of the Sylvester matrix of A and B. And a very interesting property of the resultant is that if A and B have a common factor, the resultant is identically 0. Okay? So we consider the resultant of A and B, and we first prove that the theorem holds when the resultant is an irreducible quadratic polynomial. Log quadratic, it's not a quadratic, it's of degree 3, but in this case. But if it's irreducible, then it must be that the first case holds. Okay, the first case. Then we consider the possible way that the resultant can be decomposed into components. And in each case, we prove our theorem. And finally, we need to consider the case that there is no common variable, because for me to use the resultant, I need A and B to have like degree non-zero on the same variable. So we prove the point if it is not the case, and this is where A and B are separated in some sense. I won't get into the details, but it's just like case analysis, and in any way we prove that one of the three cases holds. Okay. Any questions thus far? No. Great. So now I have this local condition, and I think now I understand it much better. I have like something I can work with, and I want to take this local condition and apply it and make it a general bound on the dimension of of my set of polynomials. So the only way, because I don't know really algebraic proof for the Sylvester-Gallai theorem, the only way that we could do it is reduce it to the Sylvester-Gallai theorem for linear forms. And okay, so there are two ways to do this reduction. First is consider the coefficient vector of the polynomials. They are vectors, and I can, if they satisfy the Sylvester-Gallai condition, then I can bound the dimension of my space. And the other is to say that the linear forms that the polynomials are defined over satisfy the Sylvester-Gallai condition. So these are the two possible reductions. In most cases, we either find ourselves reduced to one of these. Okay? Okay, so let's start. I have my set of polynomial. And then let's consider the case that every polynomial in the set satisfy case 1 of the structured theorem with at least 10th of the other polynomial. What does it mean? That with at least 10 of the other polynomials, it spans a third polynomial. This is exactly the robust Sylvester-Gallai condition for the coefficient vectors of my polynomials. So I can use exactly the robust Sylvester-Gallai and get the bound. This is like the easy case. Okay? So assume that it is not the case. It doesn't have to be that every polynomial satisfies this. So, but let's take another case and consider if every polynomial satisfies the previous condition, that means that with tens of the polynomial, it spans the third polynomial, or that with tens of the polynomial, it satisfies the third case of the structured theorem. That means that with at least tens of the polynomial, there are two linear forms that Q is in the ideal generated by those forms. So I want to conquer this case. So what do I do? First, I show that there is a bounded dimensional linear space of linear form, V, such that all the polynomials of rank 2 in Q are in the ideal generated by V. Okay? This is the first step. It's just like by any iterative algorithm that must be bound after 1 over delta steps. Okay? Now that I have this V, rank 2 tensor rank what I meant. Rank and degree. I have to. Okay. So like all the polynomials that satisfy this case with someone must be in the ideal generated by V. Now let's think about the polynomials that are not in the ideal generated by V. Okay? Then I prove that they must satisfy the original Sylvester-Gallai, because I know that every polynomial is either with 1/10 is satisfied the spanning condition, or with 1/10 is satisfied the third condition. So it takes some proof, but they must satisfy the Sylvester-Gallai theorem. So I can add them, and I get that all my polynomials are either in V or in a small set of polynomials. So to finish this, I need to bound this dimension. This doesn't have to be bounded, the intersection of Q of my set and the ideal. It doesn't have to be bounded dimension in a linear dimension or in an algebraic dimension. So I need to bound it, and we do it. We have some techniques that do it, that achieve this bound. So this is like the last step, and we bound on this case. And now let me consider the third case. So if I have a polynomial that doesn't satisfy the first case of the structured theorem with tens of the polynomial, and doesn't satisfy the third case of the structured theorem with tens of the polynomial, it must satisfy with at least 80% of the polynomial the second case of the structured theorem. And this gives me a really strong structure of those 80% of the polynomials. Specifically, they're of this form. And so I I have no other explanation. I have a very bad definition. And I prove that if my set follows the definition, then its dimension is bounded. This is the hardest part, exactly. This is like what I said so far with peanuts instead in regards to this one. So the idea here is, well, I have those AI, BI linear forms. So the idea is to bound their dimension first, and then I get that the dimension of most of the polynomial, like 80% of the polynomial is bounded. And then I work hard and get the dimension of the rest. If I have this huge structure on 80% of the polynomials, then I get the bound for the rest. Yeah, this is what I wanted to say. So this is it. This is a really rough sketch of the proof. Hopefully you will be able to read it soon once we publish it. But this leaves a lot of further research questions. So the first, most interesting one is to achieve depth for PIT. I need a colored version of this theorem. And moreover, I need to allow some sense that the polynomials are not of degree 2, a degree less than 2. Okay, because this is the case of PIT. So this is like the main theorem that we need for PIT. This is was conjectured by Gupta and BMS. And we believe that the technique that we developed, and actually we are working on it, it will be done soon. I promise you. By next year, we will have it. And this will give us depth for PIT in case the top fan-in is 3 and the bottom fan-in is 2, which is amazing. But we want to do better than this. So of course, we want higher polynomials. If we will be able to do it, we can increase the top fan-in, the bottom fan-in. Higher dimensional equivalence is the term to increase the top fan-in, like allow more than 3 sets, but 5 sets. And more than that, the condition is not that when every 2 polynomial vanish, something happened. When every k polynomial vanish, something happens. So we need to regroup everything and do it again, like work on it from. And maybe this result is works only for a 0 characteristic over C, but know that there are some similar results to Sylvester-Gallai for positive characteristics. It means especially like log bounds. It doesn't have to be a constant dimension, but the dimension is at most log n. So maybe we can do what we did here and get similar bounds on positive characteristics. So these are like the most interesting questions. And then, well, this is, for me, it's interesting. This is a purely algebraic question, which is, did we actually give a new characterization for ideals generated by quadratic polynomials? Or because we assume that there is a product of quadratic polynomials that lies in the ideal, right? But if the structured theorem holds without this assumption, that means that either the ideal is prime, or they span a reducible polynomial, or the third case. Okay, the proof that we have now doesn't work. We assume that there is a product there, but this would be a really interesting characterization of like quadratic ideals. This is interesting for many other reasons. And if it's the case, so what happened to the third case when I take the degree up? Like I said, the degree of the polynomial is 3 or 4. They're not quadratic. So we assume that the third case won't be the same. It won't be exactly what's written here, but it must be something of the sense. So this is what we like conjecture and hope to achieve soon. And that's it. Do you have any questions? Yeah.
Top line really you explained why, but the degree change, like how do you feel about it?
So, whoa. Well, it relies on it deeply. First, every time I work around decomposition of polynomials to reducible elements, then I assume that there is only one possible decomposition, AI times BI forms. If you have higher degree polynomial, you have much more room for decomposition. Like the structured theorem just essentially say that they span a reducible polynomial. This is like the real essence of the structured theorem. And in case of quadratic, if they span a reducible polynomial, they must span a product of two linear forms. In higher degrees, it will all hell break loose. And the other inside the proof, I many times I decompose like my something. Again, if the degree goes higher, then the proof doesn't work. So I don't believe that like exactly what we did would work. Just substitute and consider some more possible decomposition. I think it won't like hold as it is, but it might be worth considering. The problem is this. I went over it really fast because I thought that I'm supposed to finish now. But it's a lot of case analysis, like really, really hard case analysis. And that I spared you from. But if I allow the degree to get higher, I need more case analysis, and I have more cases. And I think that in some time I will give up. And it's not possible. It's like I won't do, in this line of thinking, I won't do constant degree, like any constant degree work. We need to understand the geometry and the algebra behind it even better. But as a mathematical, even for like, it wasn't known before. It's like a mathematical question that algebraic geometries find interesting, and it wasn't known before. So it has a really interesting underlying mathematical question, even if I forget about the PAT for a minute. So I'm not an expert on the way that Sylvester-Gallai is used for reconstruction. From what I heard, it's the point, but it requires a lot of hard work afterwards. So it's once we need the PAT to hope to have reconstruction, and once we do it, we can go and look at other proofs and see if it implies, but it won't imply it directly. We need to work at everything. It's not like a black box algorithm, except for the PAT, which is a black box algorithm. Once I give a dimension bound, I'm done. The previous PAT algorithm works just the same.
The short break will now be a long